Okay, so yesterday we took a walk down memory lane about exponential functions and logarithmic functions. We talked about how to convert back and forth between them. We talked about the graphs. We did sort of a little bit of local linear analysis, found out what the general shape of the derivative would look like. It kind of gave us a clue to what the equation might look like for the derivative. And then we talked about a whole lot of properties. I'm going to go back though to that derivative there, because then over here on the board we found that if you have a function e to the x, then the derivative is, anybody remember?
E to the x.
E to the x. And then the second derivative would be
E to the x.
And the 10th derivative is? Yeah, okay, so you get the idea. All right, so first thing, we're just going to just practice this. I don't know how we can practice, I mean, exactly say. All right, so if g of x is equal to 5 times e to the x, then the derivative, g prime, would be
5 times e to the x.
5 times e to the x. The 5, because of the constant multiple rule, any constant times a function, when you take the derivative of it, is going to be the constant times the derivative of that function. So 5 e to the x. Okay, that's pretty straightforward. What if we did something like this? I've got h of x equals e to the x squared. What about that?
Would it be 2 e to the x?
Would what be? The derivative?
Yeah.
No, not quite. Because we have to look at this as a chain rule. Outer function, inner function, okay? The outer function is e to the blah, e to the hand, all right? So, based on what we saw here, e to the x, so the derivative of e to the hand is e to the hand, e to the x squared, times
the derivative,
the derivative of the inside. So times, now the times is out here, not up here, times at this level, the base level. So now let's talk about the derivative of x squared.
2x.
That's something kind of new.
What if x was a number?
So, good question. So we'll just go with f again. So f of x equals e squared. It's really good because that's not the way that my mind would normally think. So thank you, Chloe. What is e?
A number.
Yeah, and it's approximately 2.71 something. Okay. What is 2?
It's a number.
2 is 2. Number, right? So basically, you have some number raised to a power, right? So this is essentially another number, right? You know, you can actually calculate on a calculator. Go ahead and figure out what is e squared.
Yeah.
The e button. Is that what you're asking about?
It's like 7.0.
7 point.
3889.
Okay. So, et cetera, et cetera. So what if I said, what's the derivative of 7.38 whatever? What's-
0?
Yeah, it's 0. Because it's a number. Because it's a constant. The derivative of a constant is 0. Thank you, Chloe. Y equals e to the sine x. dy over dx would be
E sine x.
e sine x.
Times cosine
Look at
x.
y'all.
Cosine x.
Man, doing chain rule, exponential, trigonometric, composition functions. Yeah, okay, yeah. Good job. So, a new formula to add in a moment to our sheet. So, the derivative with respect to x of e to the u, where u is a function of x, is equal to e to the u times, anybody?
Times the u.
U prime?
U prime.
Oh yeah.
Yep. That's one you can add to the, I think is it the blue sheet?
Yes.
Which number is it there, Chloe?
10.
Number 10 on blue sheet.
And for some reason, I didn't have the chain rule. I don't know what the other one is, but written down on like my.
Oh, on your sheet? You want so I think it's dy over dx equals dy over du times du. Is that what you're talking about?
Yes, and then the other one is d
F.
over dx. F. Yes.
It was the derivative
Yes.
of that. The derivative of f composed of g. That's f prime with g of x all by its lonesome inside left intact times the derivative of the inside. Does that make sense?
Yes.
It's the outer, derivative of the outer with the inner intact times the derivative of the inside.
And then is that a u on top of du over dx?
Yep, that's
Okay.
u. So it's the derivative of the outside with respect to u, then derivative of u with respect to x.
Thank you.
You bet. I must say, now I don't know if I really pointed it out, but well, the derivative of e to the x, d to the x, when we did this analysis, and we noticed that this is the graph of e to the x, we noticed that the derivative shape was roughly that same shape, right? So, okay, great. Let's do some more stuff. Let's do the derivative of a number that is not e to the x. So let's say g of x equals b to the x. And let's find the derivative of that. Now what I'm going to do here is find the thing that I showed you yesterday. I said b to the x can be written as e to the ln of b to the x. And that can be written as e to the x ln b. And you were like, okay, why is that? Well, we said e to the ln b of x is equal to question mark. Anyway, so we kind of worked through that. But all that to say is that b to the x can be written as e to the x times ln b. So now, let's take the derivative of that. The derivative of e to some function is going to be
E
e to some function, so e to the x times ln b times the derivative of this. Oh my gosh, what is the derivative of x times ln b? Alright, so x times ln b. Now, I know y'all are not crazy comfortable and familiar with natural log, but natural log is a process, is asking what's the exponent of e, then, you know, whatever. E is the base, and this is the power, whatever. Anyway, The ln(b) is a number. It's a constant. Okay? Take the natural log of 5, you're going to get a number. Natural log of 50, you're going to get a number. Natural log of anything, you're going to get a number. So that's a number. Okay? So in reality, it's the same as if you were saying x times 5. What's the derivative of x times 5? No.
It's
5.
fine.
No.
You're normally used to me saying what's the derivative of 5x. Okay? Do the derivative. Okay? Just because that's a linear and the derivative of linear is a constant. Okay. So the derivative of x times ln b is ln b.
Oh yeah, because it's like LNB to LB, LNBX.
But if, yeah, it's really more like here's ln b times x. That's a number. What's the derivative of a number times x? Answer, the number. So chain rule is the derivative of that thing up there, so it's just ln b. Okay? Well, here's a weird thing. E to the x ln b is what I said is what b of x was. So g prime of x is equal to b to the x times ln b. Alright, so if f of x equals b dx, then the derivative is b to the x times ln b.
Can we put that for 12?
Yes, we will. Number 12 says, what is the derivative with respect to x of, is it b to the u?
It's a to the u.
A to the u for whatever reason? Okay, that's fine. A to the u, a is a constant, b is a constant. Yep. So, Rosa, what would it be there?
It's a to the u times ln a.
Almost done. Times.
U prime?
Yep.
Oh man, so everything is U prime, right?
Pretty much, because it's a function of
U.
yeah, and then u is a function of x.
Nice. That one makes sense.
The plan is that these two are going to be options on your memorization quiz tomorrow.
Oh no.
Okay? Shall we make it just derivatives tomorrow? Just derivatives tomorrow.
Yeah.
How's that? Okay. Now, for those of you that are just into this kind of thing, there's a lot of similarities between these two, right? Derivative of e to the x is e to the x. Derivative of b to the x is b to the x times ln b, right? Okay, so if you can remember this, then anytime you don't have e as the base, then you just remember, okay, it's the base to the power, but then times natural log of that base, okay? Now, this is where it's interesting. Actually, this is the more generic example. This is the more generic because
You could use it on the.
we could apply it up here, right? Because e is a number, is a constant, just like any of these, okay? And so you're like, well then why didn't we put ln e right here?
Because the ln e is 1.
Because it's 1.
Yeah.
Wow.
So you could. So this actually is the more generic version, okay? However, if you're like me, I actually remember this more than I remember this. So I just remember that, okay, derivative of the x is e to the x, and the derivative of any other base to the x is, it's like e to the x, but I gotta multiply by something. Oh yeah, ln b.
Oh, what's generic?
Generic, sort of like more general.
Oh.
Sort of like the word person rather than the word detector.
Oh.
Okay, so the memorization quiz tomorrow will be.
Just blue sheet, no, not that one.
Okay.
Just blue sheet. Let's go and do some problems together. That one's for Chloe.
But what if I say to them because it's not good?
Go ahead and at the table start working through some of these. Alright, let's pick one on that front page. Fine. There we go. Differentiate each function with respect to x. Okay. I guess number one's a good place to start. The derivative of e to the 5x to the 6 would be
E to 5x to 6 times 30
times 30x to the 5th. Let's see if you're right. E to the 5x, yeah, it's not gonna hard to see here. 30. I think we're on the right track.
So which ones are the ones where you can take that, like the exponent and multiply it to the, like the base of the exponent? Like if you have a power raised to another power, and then you were to multiply, like if, for example, if you were to multiply the 6 times the 5x on the exponent, like I know in that case you can't do it, but like what is the case where you can?
Okay, so you're talking about the difference between the power rule and the exponential rule. Okay, so there's a difference between f of x equals x to the 6th and g of x, which is equal 6 to the x. So this is a polynomial. It has the base is x, and the exponent is a number. And you apply the power rule. I don't know if this is answering your question. So that's 6x to the 5th. This is an exponential function, where the base is a number and the exponent is a variable. And the derivative is 6 to the x times ln 6. Am I making sense?
That makes sense. What I was asking was, let's see if I can find an example of it. Oh, like for example, like in this one in my notes it says b to the x equals e to the natural log of b, and then if you have that raised to the x power, you said it's the same thing as e to the x.
Right. The only reason why I told you that was for us to be able to derive this formula. That's the only reason why I told you that. You really don't need to apply that property at all. The only thing that you need to apply for this homework, for the most part, are these two rules.
Okay.
So like all those other properties, I was telling you those so that when I said b to the x is equivalent to e to the x ln b, and then we took the derivative of it, that property was for us to then be able to take the derivative of it and then simplify it to be able to get here.
Oh, I see.
Yep.
So like in the back grade, on like number 11 and 12 on algebra,
Oh my gosh, yeah, that's kind of weird. Is that even realistic, or is this just a case of like mathematicians just being like, look what we can do it now? All right. Yeah. There might. I don't know. I don't know every single discipline in the world yet, and how every single math formula could relate, and whether or not there's some things that are just right now like pure math, and there's other things that are like, yeah, we deal with this kind of stuff every day. I don't know. I will tell you though that kind of raises an interesting point. Like for instance, if you plan on going into, depending on what field you're going into, like I'll just throw engineering since that's one I'm super familiar with. Okay, so if you're gonna go into engineering, you have to take calculus 1 and 2 and the differential equations and so on and so forth. Well, there's a lot of schools that they're at the university, like they have different schools. There's a school of engineering, the school of biology, arts and sciences, and stuff like that. So the engineering professors and the engineers were like, we don't need the math teachers teaching calculus to our future engineers, because math teachers are going to throw stuff like this just to see if you really know it. We really want them to be able to be competent enough to be able to handle some basic stuff, but then do some problems that are maybe not so nuanced, not so specialized, not so abstract, but a little bit more concrete. We'd rather them know, you see what I'm saying?
Mm-hmm.
And so they end up having the engineering professors teach the calculus. You know what I'm saying? And if you're going to the medical field and you have to take Calc 1 and Calc 2, then maybe sometime there might be some similar situations. I don't know. Normally they just be like, just take Calc 2, just get it done. I'm sure there's a reason why doctors have to take Calc 2, but I'm not familiar with that field and I don't know why. You know what I mean? Yeah. But I know that my family practitioner had to, because when I go to see him, we talk about math. It's Calc 2 experience. Because that's what we talk about. Anyway, so all right. That being said, you need to treat this thing like just its own, function up there.
Oh.
So dy over dx. So the derivative of e to the anything is
E to the
anything. So e to the 10x squared times
e to the 10x squared.
Okay, so yeah, so I'm basically new problem here now. Take the derivative of e to the 10x squared. So that's going to be e to the 10x squared, right?
Yeah.
Times
20.
20. Yeah.
20x. Now notice where I'm putting the dot there. I'm putting the dot there, string it along chain rule.
Okay.
So it's basically the original guy times the derivative of the exponent, which the exponent happens to be the entire function. Well, derivative of the exponent, so it's going to be that. That's absolutely right.
Wow.
What about the e on the bottom?
This one right here?
Yes.
So it's e to the blah, right? So the derivative of e to the u is going to be e to the u times u prime. So right now, my hand is taking the place of the u. So the derivative of this is e to the u, which is what I've got. Here's e to the u, e to the hand. And then all of this is the u prime.
Oh,
All of
okay,
this
that's
is the
u prime,
derivative
okay.
of that.
If we go over 5 base
So I mean, that whole thing from the equal sign to the right is all the derivative of,
Which do that one?
that's all part of the derivative of e to the,
Oh, that's one.
e to the next third.
Maybe. Do another one and we'll see if you're on the right track. Alright, and we're gonna do one or two more and then I need to show you how to do the derivative of logarithms.
How do you do?
I want one more question. One like which one? 5? Okay. When you look at that, what are you thinking?
Take the derivative of the first, and then you take the derivative of e to the x to the 10.
Okay, so or keep the first
Yeah, and then keep
first
the
times the
second.
derivative of the second plus second
Yeah.
times the derivative of the first. Emily said product rule. Product rule is right. Or you can distribute and then do product rule
So
anyway.
like the the x to the a becomes a, that would be like the first, and then the e, okay.
Good stuff. Anything out down here in the depths? Oh, I didn't go another level. Y'all are lucky. On some of my previous, we had like e to the e to the e to the.
Come on.
Yeah. Are we good with that?
I think you're the
Gotta have another
one
home
with
sheet, so I can-
once we switch to e for numbers, like 3 to the 5 x
Do we
squared.
have any of those?
Yeah.
Oh, okay. So like number 9?
Yeah. So the 2 take the place of e.
Yeah. Okay. So it's 2. So that it's a number to a power. So we're going to apply this one right here. So the derivative of 2 times 5x cubed is literally it's just 2 to the block times.
The derivative.
Well, hold on. ln b.
Oh yeah.
So I want to make sure I don't forget that. So ln 2, and then times, as you were saying, Ivan.
The derivative of the exponent. So
Exactly.
15x.
There she is. And that concludes today's lesson.
Serious?
And then tomorrow we do logarithms? Sure. All right. That way, if y'all have any questions, I can check them. We good?
Yes.
All right then. You have the rest of the class to work on this problem.
Is this
This is due tomorrow.
Turn in my direction.
Thanks for watching. Today we talked about the derivative of the exponential functions and, well, that's it. The exponential functions and exponential functions in general. Thanks for watching.